It's minus 40 degrees outside. The wind is hitting the metal walls like a freight train. And inside this Quonset hut, a man is sitting on a bucket, fully dressed in his winter gear. He thought he found the affordable answer to Alaskan living. Watching his breath turn to fog, he spent $28,000 building this structure. He thought he was smart. But right now, his fingers are going numb. Ice is forming on the inside of his walls. His heating bill last month was $847, and his floor, so cold it hurts to stand on it barefoot for more than 3 seconds. He's not in a survival situation. He's in his home, and the worst part? Everything he did was technically correct. He followed the instructions. He bolted the arch panels together exactly the way the manual said. He installed a heater. He thought he was done. But nobody told him about the one thing that separates a Quonset hut that works from one that slowly destroys you every single winter. Nobody told him about the thermal break. And that single missing layer, thinner than your hand, is the difference between an $847 heating bill and a $94 one. It's the difference between ice on your walls and a warm, dry, livable space. It's the difference between a structure that fights you and one that actually works. Smart Alaskan builders figured this out years ago. They don't talk about it loudly. They don't post about it online. But if you walk into their Quonset huts, the ones buried under 3 feet of snow, you'll feel it immediately. It's warm. It's quiet. It smells like cedar. And the walls are completely dry. What they know, and what most people building Quonset huts have never been told, is exactly what you're about to learn. Stay with this, because by the end, you'll understand the full system, layer by layer, and you'll never look at a metal arch building the same way again. Let's start with the enemy. And the enemy is physics. Steel, the material your Quonset hut is made of, is one of the worst possible materials to separate you from a brutal cold environment. It conducts heat approximately 50 times faster than wood. 50 times. That means if you build a wall out of steel and a wall out of wood, and you heat both interiors to the same temperature, the steel wall will bleed your heat to the outside at 50 times the rate of the wooden one. Your Quonset hut is essentially a giant steel tube sitting in the snow. Every BTU your heater produces, every dollar you spend on propane, on electric heat, on wood, is in a race. It's racing toward the metal skin of your building, and once it gets there, it's gone, conducted straight through the steel, and handed directly to the freezing air outside. This is not a flaw in the design of the Quonset hut. The arch shape is actually brilliant. It's self-supporting. It handles massive snow loads. It goes up fast. It lasts for decades. The United States military built hundreds of thousands of them for a reason. But the military wasn't trying to live in them comfortably at minus 40. They were storing equipment. They were parking vehicles. They were using them as temporary structures. When you try to make a Quonset hut into a home or a heated workshop or a livable cabin, you're fighting the thermal properties of steel with nothing but a heater. And the heater will lose every single time. You'll run it constantly, spend a fortune, and still be cold. But here's what changes everything. Heat doesn't just move through conduction. It also moves through radiation and convection. And when you understand all 3 paths that heat escapes your building, you can block all 3 of them with one intelligent layered system. That system is what Alaskan builders quietly call the thermal break stack. And it starts with material most builders either skip entirely or apply completely wrong. Closed cell spray foam. Not the stuff you buy in a can at the hardware store. Professional 2-part closed cell spray foam, the kind that expands, hardens, and bonds directly to the steel surface of your Quonset panels. This is layer 1, and it's doing 3 jobs simultaneously, which is why skipping it is such a catastrophic mistake. First, it stops air infiltration. A Quonset hut has dozens of seams where arch panels overlap. Each one of those seams is a potential air leak. Cold air finds every gap. Spray foam seals every single one permanently. The moment you coat that inner steel surface with foam, you've created an airtight thermal envelope. Second, it acts as a vapor barrier. This is the one that destroys buildings people don't treat seriously enough. When warm, humid interior air contacts a cold steel surface, it hits its dew point and condenses into liquid water. That water runs down your walls, pools on your floor, soaks into anything it touches, and in freezing temperatures, it turns to ice. inside your building. On your walls, the ice expands. It damages finishes, creates rust pathways on the steel, and introduces a permanent moisture problem that only gets worse every winter. Closed-cell spray foam, applied directly to the steel, keeps that steel surface from ever being exposed to interior air. No contact, no condensation. Problem permanently solved. Third, and this is the part most people don't realize, closed-cell spray foam has a genuine R value. At 2 inches thick, you're sitting at approximately R14. At 3 inches, you're closer to R21. That alone is better than a standard insulated residential wall from 30 years ago. But R21 is not enough for Alaska, not even close. So you don't stop there. Once the spray foam has cured, and you need to give a full 24 hours, don't rush this. You install your furring strips. This is layer 2, and it is the actual thermal break that gives this whole system its name. Furring strips are thin pieces of wood, typically 1 inch by 3 inch or 1 inch by 4 inch, that you fasten to the now foam-covered steel arch. You run them parallel to the length of the building, spaced about 16 inches apart, following the curve of the arch, which conducts cold at a fraction of the rate that steel does. When you mount with a foam-covered steel, you've created a complete interruption in the thermal pathway. Heat can no longer travel in a straight line from the warm interior through to the cold steel. It has to navigate through wood, through air gaps, through foam, and each transition steals more of its energy. But that's not even the main benefit of the furring strips. The main benefit is what they create. Between each pair of furring strips, running the full length of your building, you now have a cavity, a channel, a dead air space between the foam and wherever your finished interior surface will eventually go. Dead air is one of the most underrated insulation materials on the planet. Still, air conducts heat terribly. That trapped air pocket between your furring strips adds meaningful R value. And more importantly, it gives you somewhere to put layer 3. Layer 3 is where your R value explodes. Between those furring strips, you pack mineral wool bats. Cut to fit, pressed in tight. No gaps. If you've never worked with mineral wool, you need to understand why serious builders in extreme climates choose it over fiberglass. Mineral wool, also called rock wool or slag wool, is made from volcanic rock and industrial slag spun into fibers. It does not absorb moisture at all. You can submerge it in water, pull it out, and it will dry and perform exactly as it did before. Fiberglass, when it gets wet, loses most of its insulating value and becomes a mold risk. In an environment where any moisture infiltration is possible, and in Alaska, it is always possible, mineral wool is not a luxury. It is the correct choice. Mineral wool also has a higher fire resistance than fiberglass. It doesn't melt or shrink away from flames the way fiberglass does. In a structure where you're running heating systems hard all winter, that matters. The R value of mineral wool bats in a standard 3.5-inch cavity is approximately R15. Add that to your R14 to R21 from the spray foam, and you're already at R29, R36 before you've even installed your interior finish. But you still have one more layer. Layer 4 is the one that makes people stop and stare the first time they walk into one of these builds. Tongue-and-groove cedar or pine paneling, installed over the furring strips, covering the entire interior surface of the arch. There's a reason Alaskan builders choose cedar specifically. Cedar is naturally resistant to moisture. Its cellular structure contains oils that repel water and inhibit mold growth. In a cold climate building where moisture management is everything, cedar isn't just an aesthetic choice, it's a functional one. Pine is a solid alternative and significantly cheaper. If your moisture control in the earlier layers is solid, pine performs beautifully and gives that warm, cabin-like interior that makes a Quonset hut feel like a real home rather than a military surplus building. The wood paneling adds another R, 1 to R, 1.5 depending on thickness. That sounds small, but combined with the other layers, you are now looking at a completed wall system achieving R30 to R40 total. That is the equivalent of a well-insulated modern stick-frame home. Inside a structure made of corrugated steel, the transformation is not subtle. Walk into an uninsulated Quonset hut in winter, and you can see your breath within 30 seconds. Walk into one built with a thermal break stack, and it feels like walking into a log cabin. The smell of cedar hits you. The walls are completely dry. The temperature is stable. The heater is barely running. That's not magic. That's physics working for you instead of against you. Now here's where builders who understand the shell system still make expensive mistakes. They nail the arch insulation perfectly, and then they completely ignore the three other areas that will undermine everything they built. The end walls are the first one. A Quonset hut has two flat ends, the gable ends, that close off the arch. These are not curved. They're typically framed with standard lumber, and a lot of builders treat them as an afterthought. They throw up some fiberglass bats and call it done. That's a serious problem. The end walls are where you put your doors and windows. Every penetration through an insulated wall is a potential thermal bridge, a direct path for heat to escape. Your windows need to be triple pane in a climate like Alaska's interior. Your door frames need to be thermally broken at the rough opening. And the end wall framing itself needs to be built with a technique called advanced framing or optimum value engineering, which reduces the amount of wood in the wall and therefore reduces thermal bridging through the studs themselves. Every stud in a wall is a thermal bridge. Wood is a far better insulator than steel, but it still conducts heat. Every place a wooden stud contacts both the inside and outside of your wall, heat leaks through. Advanced framing minimizes those contact points. In an extreme cold environment, this detail alone can be worth hundreds of dollars a year in heating costs. The second area builders ignore is the floor. A concrete slab sitting directly on frozen ground in Alaska is not just cold, it's a refrigerating system. The ground below is often permafrost, permanently frozen soil that will actively pull every BTU of heat you pump into your building straight down through your slab and into the earth. In-floor radiant heating is not a luxury in this application. It is the foundation of everything. A network of PX tubing embedded in the slab, circulating warm water from a boiler or water heater, turns your floor from your biggest enemy into your most efficient ally. Radiant heat from below rises gently through the space. It warms objects and people directly, rather than heating air that immediately stratifies and pools near the ceiling. Pair your radiant slab with 2 inches of rigid foam insulation underneath the concrete, installed before the pour, and you've broken a thermal connection between your heated slab and the frozen earth below. Now your heating system is actually heating your building instead of heating the permafrost. The third area is ventilation. This is the one that surprises people most. You just spent significant money and effort making your building as airtight as possible. And now the advice is to deliberately introduce fresh air? Yes, absolutely. And here's why. A perfectly airtight building without mechanical ventilation will poison you. Carbon dioxide builds up from human respiration. Humidity from cooking, showering, and breathing accumulates until fine somewhere condense. And in a cold building, that somewhere is always somewhere you don't want moisture. Cooking fumes concentrate. If you're running any combustion heating, the risks multiply. The solution is a heat recovery ventilator, an HRV. It's a small box, typically installed near your ceiling, that simultaneously exhausts stale indoor air and draws in fresh outdoor air. The critical feature is a heat exchange core inside the unit. As the outgoing warm air passes the incoming cold air, the HRV transfers up to 80% of the heat from the exhaust stream to the incoming fresh air stream. You get full fresh air ventilation with only 20% of the heat loss you get from simply cracking a window. In a well-sealed, properly insulated Quonset hut in Alaska, an HRV is not optional. It's the system that makes everything else sustainable for human habitation. Let's talk about real numbers, because this is where everything becomes concrete. An uninsulated or poorly insulated Quonset hut in interior Alaska, somewhere like Fairbanks, where winter temperatures regularly hit -40 and sometimes push past -50, will cost between $600 and $900 per month to heat, and it will still be cold. Builders who've been through this describe it as burning money to be uncomfortable. A Quonset hut built with a full thermal break stack, spray foam, furring strips, mineral wool, cedar finish, insulated slab, HRV, runs between $80 and $150 per month in the same conditions, same outside temperature, same square footage. The difference is the system. The cost to install the complete thermal brake system runs approximately $4 to $8 per square foot of interior surface area, depending on material costs and whether you do any of the labor yourself. For a standard 30 by 50 foot Quonset, a common size for a small home or large workshop, you're looking at somewhere between $6,000 and $12,000 in materials for the full insulation stack, at an average heating savings of $600 per month. Conservative, based on real builder reports. That investment pays for itself in 10 to 20 months, less than 2 Alaskan winters. After that, every winter is pure savings. Every month the outside world is paying $700 to heat a poorly built structure. You're paying $120. The thermal brake doesn't wear out. It doesn't need maintenance. You install it once, and it works for the life of the building. There are a few final details that separate a good cold climate Quonset build from a truly excellent one, and they're worth knowing before you start. Door placement controls more of your heating load than most people realize. A door facing north in Alaska is facing the direction of your coldest prevailing winds in winter. Every time that door opens, a wall of Arctic air enters your building. Orienting your primary entrance to face south or east dramatically reduces that infiltration. Better still, build an airlock vestibule, a small enclosed porch structure outside your main door with 2 doors in series. When someone enters, they open the outer door, step into the vestibule, close the outer door, and then open the inner door. The vestibule acts as a thermal buffer. The brutal outside air never directly contacts your conditioned interior air. This single addition can reduce your heating load by 10 to 15% in a high-traffic building. In a home, where the door might open dozens of times per day, that adds up to real money every winter. Window selection matters enormously as well. Triple pane windows with a low-E coating and argon or krypton gas fill between the panes are the baseline for serious cold climate construction. The low-E coating reflects radiant heat back into the room. The gas fill reduces convective heat loss between the panes. A high-quality triple-pane window in Alaska performs 4 to 5 times better than a standard double-pane unit. For a small Quonset with a modest window area, upgrading from double to triple-pane might add $2,000 to $4,000 to your build cost. In Alaska, that pays back in approximately 1 winter season of reduced heating costs. Finally, and this applies specifically to Quonset huts in high snow load zones, understand the structural difference between the arch and the end walls when it comes to snow. The arch is brilliant in snow. The curved shape causes snow to slide off naturally once accumulation reaches a certain depth. You rarely need to shovel the roof. But the end walls take the full brunt of wind-driven snow, and they carry the point load from the arch itself. These walls need to be engineered and reinforced appropriately for your specific snow load zone. Alaska has regions rated at 100 pounds per square foot of roof snow load, or higher. Your end wall framing and foundation connection points must be designed for those numbers. This is not an area to estimate or guess. Pull the local building code requirements for your specific area and build to them. The man sitting on the bucket in the freezing Quonset hut at the beginning of this, he's not a bad builder. He's not stupid. He just didn't know what he didn't know. And in Alaska, in winter, what you don't know can genuinely hurt you. The Alaskan builders who figured this out years ago, the ones with warm, dry, cedar-lined Quonset huts running on $100 a month in heating, they're not doing anything exotic. They're not using materials you can't get. They're not applying techniques that require specialized training beyond what any competent builder can learn. They're just doing the layers in the right order. Foam first, wood second, mineral wool third, cedar fourth, slab insulation, radiant heat, HRV, triple pane glass, airlock entry, proper end wall framing. Every single layer has a job. Every layer makes the next one work better. And when the whole stack is in place, something remarkable happens. The building stops fighting you. The heater stops running constantly. The walls stay dry. The air smells clean. The floor is warm under your feet. And outside, it's still minus 40. The wind is still hitting the arch panels. The snow is still piling up at the base of the end walls. But inside, none of that reaches you anymore. That's what one hidden layer, one deliberately interrupted thermal pathway through a steel wall. Actually does. That's the Alaskan secret, and now you know it.